Hello and what's up to you all awesome and wonderful matriculants. My name is Abram and we're together in this wonderful evening. I hope you've learned so much at school. If you haven't, trust me, we're here to twist and turn your mood around and make sure that you learn more and learn extra today. Of course, I'm with John today. John, how are you?
I'm great, guys. Great to be with you again, and we're really excited because we've got a fresh topic. We've been doing some mechanics up until now. We're moving on to something that hopefully you've started to deal with at school, dealing with wave, sound, and light. And tonight we're dealing with the Doppler effect, which is a really interesting phenomenon and has applications all around us. So stay tuned, don't go away, and make sure you get the notes. Abram will tell you about where to get them.
I'm so excited already, John, and I've seen the vibe on the page and on Twitter. Skills is already saying, I can't wait for the show. They saw your picture, actually, and yeah, they can't wait for the show. Well, guys, because I'm a nice guy, I've already posted the notes for you, so go to facebook.com/learnextra, and they'll take you directly to our view option or the download link option. But if you can't see them on our Facebook page, make sure that you go to our website, which is learn.mindset.co.za. Otherwise, follow us on Twitter @LearnExtra, and I'll give you the links directly. Remember, guys, the notes that we have for you are extracted from this workbook, of which you can get for only 139 Rand. Simply email sales@mindset.co.za and ask more about it, or place in your order. John will tell us more about it.
Okay, guys, so let's get going now. We're going to talk a bit about the workbook in a minute, but let's get straight into the Doppler effect. And I'm going to start with something off the top of my head and something that happened during the last week. And it says a challenge question, which AB's posted on the page as well. Not the normal type of challenge question. This one says, what scientific tool had its 25th birthday on the 24th of April 2015? So get onto the page, put down your answer, what you think it might be. If you've answered already, then here's the extension to the challenge question. Start to think about it. What has this tool got to do with the Doppler effect? We'll come to answer that in a little while. Okay, so let's get into some discussion about what is the Doppler effect. So Doppler, it's not somebody that goes around drinking Dop all the time. That's not a Doppler effect. No, we want to make sure that you understand. Doppler was the name of a scientist, and he discovered something very interesting. As part of the properties of waves generally, whether they be water waves, whether they be sound waves, whether they be light waves, they have this very special characteristic. Let's have a look at it and see what it says. So it says that it's the apparent change in the frequency of a wave if the observer and the source are moving relative to one another. Sure. Guys, that's quite a mouthful. So let's try and break it down for a moment. The source of a wave is where it's produced. So the machine that is making waves. Now remember, waves can be generated from an oscillating source. A source that vibrates up and down, left to right, and it produces some sort of output that travels through the medium, whether that be electromagnetic waves, or whether it be sound waves, or whether it be water waves. They all move in this particular region. Now, the frequency, remember, is the time, the number of vibrations, complete vibrations in 1 second. So if the oscillator goes up and down in 1 second, we'd say it has a frequency of 1 hertz. But if it does this motion 3 or 4 times in a second, say 5 times in a second, we'd say its frequency is 5 hertz. Hertz is the unit of measurement, the SI unit of measurement for frequency. So what it says is this. The source is vibrating. We know the source can't change its vibration. But because the source is moving relative to an observer. So here we've got a situation. Let me explain what that means. So we've got the source moving over here, and we've got somebody standing over there, and they're moving at the same speed. Well, the distance between them is exactly the same. There's nothing changing. But if the source is stationary and the observer moves towards the source, or the person is stationary and the source moves towards the observer, then there's relative motion between the two. So please understand that. It's under these situations, under these circumstances, that we will try and we will apparently hear not the frequency, or we will not observe the frequency of the source, but we will observe either a greater or smaller frequency depending on some conditions. Now that all sounds a little bit strange, but let's just try and illustrate it first of all. And because I like visual stuff, I'm going to show you one that you might not have seen in your textbook, and that's dealing with water waves. In fact, this little video on water waves is, or on the Doppler effect and showing water waves, is on the Mindset website. So go to Learn and check out Physical Sciences. Look for Doppler effect in everyday life, and it's lesson number 1, and you'll see it. So what have I taken here? This is a ripple tank, and it has made shadows where there are ripples. Okay? There's a light shining underneath, and what I'm hoping to show you here is there's the oscillator. There's the little thing that's going up and down. And hopefully, I've just traced around those shadows. You can see there's another one over there, and there's probably another one in between there. The photo isn't that good. I've just taken a screenshot of the video. If you look at the video, you'll see it a little bit clearer. But what we're seeing is that these are all concentric. They are evenly spaced as much as we can. Okay? You don't see a distortion. They're staying the same distance away. Now that's very important. The distance between the shadow, that distance, and that distance, and that distance, that's referred to as the wavelength, because they're two successive crests. They're consecutive, they're next to each other, and they're two different crests, or two different troughs. And so we've got a visual way of seeing wavelength. Now, wavelength is related to frequency. If the wavelength is very small, the frequency will be very high, because we'll have more wave fronts passing a point in a second. So understand that. Wavelength is very long, frequency is low, because we're not going to get as many complete waves in 1 second passing a point. So that's what it looks like when we've got a stationary source. So that source there was stationary. Okay. Now, I want you to look at the next photo that I've taken. And hopefully you can see that there's something different here. I'm going to trace over it just like I did the first one. And I'm not going to try and cheat or do anything here. I'm just wanting to get those regions in so you can see that there's a difference. Notice something here, that between this point over here in the front compared to those points over there at the back, can you see there's a smaller gap? Abram, would you just look here for a minute and confirm for me that the gap here is small and over here it's large?
Yes.
Do you agree?
Yes.
It's not in a smooth circle. Okay? They've kind of bent. Now the reason for that is that source, that was the source, was moving in this direction. Okay? So what we see is in the front of the moving source, the waves are closer together. They're squashed, they're bunched up. So that at the front, they have a high frequency, high F, where at the back, they have a low frequency. Now notice low frequency, long wavelength, small wavelength, high frequency. So guys, here we've got the key of the Doppler effect. Apparent frequency, apparent observed frequency. Depends on in which direction we are moving relatively towards the source. If we're moving towards the source, or the source is moving towards us, then we're going to experience a high frequency. If we are moving away, or the source is moving away from us, we're going to experience a low frequency. So high means towards. Low means away. Now you can think about how about thinking about something to stick that in your head? Either make up a little rap or make up a couple of words. I don't know. I mean, you guys are so bright out there. I'm sure you're going to come up with, if it's high, then it's towards, and away is low. Something like that. You think about it. See if you can remember it. Okay. Now, next point. Because this is where we sometimes have problems. And I want to just take you over this formula. Formula on the data sheet is quite complicated. And people get in a whole lot of fuss about the formula. First thing I want to say to you is it's got two parts. And I'm going to rewrite it so that it's clear for you. It's got the frequency of the listener or of the observer. And the reason we use listener is most of the time we don't use water waves, we use sound waves as an example of the Doppler effect. But it happens in water waves. And it happens in other waves as well. So the frequency of the listener, then we've got this part in brackets, and then we've got the frequency of the source. So F with a subscript L is frequency of the listener, frequency with a subscript S is the frequency of the source. And in the middle here we've got a fraction, and this fraction is a little complicated. But I want to explain to you either that fraction is going to be smaller than 1, or it's going to be bigger than 1. Okay? Let me say that again. This bit is either going to be bigger than 1, or it's going to be smaller than 1. Let's try and predict. If this is bigger than 1, so if that bit is greater than 1, then I'm going to have a number greater than 1 multiplied by the frequency of the source. What's that telling me about the frequency of the observer? Remember what we said? When the frequency is higher, then it's moving towards us. So when we say this number here is bigger than 1, then we can immediately say it's towards. Okay. I'm either moving towards the source or the source is moving towards me. But what happens if this is a fraction and it's less than 1? If it's less than 1, if this part here, this part in brackets, and I haven't even got to it, if it's less than 1, so 1 is bigger, the crocodile's snapping to 1, it's less than 1, less than, then we can say then it's moving away. I'm either moving away and the source is standing stationary, or I'm stationary and the source is moving away. So you've got to just not plug in something to a formula without thinking. You've got to start understanding what that formula is all about. The next thing I want to say to you, it's a very simple thing. It says the velocity of sound plus or minus the velocity of the listener as the numerator on the top of the fraction over the denominator, velocity of sound plus the velocity of the source. Now, in the data sheet, it gives it to you like this. Guys, listen to me carefully. In your final exam, or in your June exam, and in your prelim exam, and in your final exam, or even in your class test that's coming up, you must write out this full formula. Don't just say, well, I think it must be, and I'll drop some signs. Write the full formula out with the plus and minus. From the information that you're given, you can then decide what is stationary, what is moving towards, what's moving away, and decide whether it's a plus or a minus. Because here's the thing. If we want this to be bigger than 1, then the numerator must be bigger than the denominator. If we want it to be less than 1, then what are we going to say? Then the denominator, the thing at the bottom of the fraction, must be bigger than the numerator. Try and reason it out for yourself and understand it. In the notes, we've summarized for you very clearly what needs to be plus or minus depending on whether it's moving towards or away. I find it easier to think it through. So we'll come to that when we do the formula. Right. Now, Abram, I know you've been waiting for this because what we're going to talk about is sound. Okay. Now, the thing that I know about Abram that you might not know is Abram's played in a band. Okay? And he's quite cool in terms of his musical instruments, but he's even better in terms of singing. Okay? So we're not going to ask him to sing, please no, but we know that he can hit the really high notes. Okay? He sings really high. We won't go into that, but what we're going to say as far as sound is concerned, frequency is related to pitch. So you get high and you get low, okay? High notes and low notes. The higher the note, the higher the frequency. The lower the note, the lower the frequency. Now, please understand that frequency is not the same as loudness. We can talk very softly and we can talk very loudly. That's not the difference between frequency and pitch. Okay? Loudness is related to the amplitude and to a certain extent the energy of the sound wave. Okay? The amplitude is related to loudness. What we're interested in the Doppler effect is all about frequency. So we're going to look at frequency now. Now, if we want to make a sound, you can make a sound from anything. Lots of different types of musical instruments. But this one is just a piece of tube, old pool pipe from a creepy. And if I swing it, I'm going to get a vibration of air molecules inside here as the air rushes through it, just like a wind instrument. But here's the interesting thing. What I'm going to put up is on the floor in front of me, I've set up a microphone. And I'm going to start to swing this so that it moves towards the microphone and then moves away from the microphone. Moves towards the microphone, moves away from the microphone. Okay? And in a second, James is going to drop my mic and I'm going to get into a full swing and see if you can hear what happens as we get this pool pump or this pool noodle, whatever we want to call it, hose to make a little bit of noise. You could try this at home if you've got a piece of thinner pipe. I just want to make something that looks big. And let's see if we can get it going. Right, Abram, you ready?
Yeah, I'm just being careful. Hey?
Okay, I want you to observe. Tell me what you hear. I'm going to try and do it as loudly as possible, but sometimes it's not so loud. But let's just give it a go. Are we ready? James? Did you hear anything?
The sound was just going up and up and up and up and up.
Just going up. There was no dropping.
When the more you rotate, the more it goes up and then it drops down.
Did it drop up? Did it go up
Yes.
and down?
Yes. Up
Could you
and
hear
down.
the high note and the low note?
Yes.
Okay, just in case we didn't hear it, I'm going to try it one more time.
Cool.
But this time I'm going to stand this way. And hopefully I'm not going to knock the board. I'm also going to change the length. So let's go. Now that didn't work as well. So let's try it again. I think we've given it a go.
Yeah.
How about you? What did you hear? Hope you've heard something. Hope you've heard that whoosh noise squeaking at times and dropping down as a low note. That's an illustration of the Doppler effect. If you didn't hear it, then I'm going to challenge you to get somebody to swing a rope for you and do the same thing.
I think we should take a break on that note.
You think we should take a break because I'm out of breath?
Yeah, because you
Oh.
really need some break.
You know what, Avram? Thanks very much. There's just one little thing I need to say before we take a break, because I can see we're out of time. Applications of the Doppler effect are in the notes, but the main one is looking at blood and looking at the speed. And another one is related to speed. They sometimes use it together with radar and speed of vehicles. And the last thing is the dentists love to use it to clean your teeth. So those are all ultrasound and Doppler. Sorry, that's not Doppler. that's just an ultrasound thing. So there are applications of the Doppler effect. Guys, check the notes out, get the book, because this is all information that you will miss if you don't get the book. Abram.
Yeah, I joined at some point. I think you were gonna cry, but I think you deserve a break, guys. It's a very, very fun lesson. I can't wait to get more from John. And guys, keep your comments coming, because after the break, I'll take some of your questions as well. See you soon. Now, guys, you've just seen a nice promo telling you about the awesome competition which we have about South Point accommodation. Yes, for you, matriculants. So if you're thinking of going to varsity next year, think about accommodation as well. But if you haven't thought about it, all you need to do is to enter our competition, and you could win for yourself 1 year's free accommodation, courtesy of South Point accommodation. All you need to do is to fill in the entry form on our website. I'll post the link just for you on our Facebook page. John, I've got some great feedback from the Mind Cities, and I just want to share these few ones.
Yeah,
before
I'm
we get to
sure
your
that I'm
questions.
unfit. I know, guys, I know. I've been sitting behind a desk all day. Okay, let's hear it.
I didn't say anything. Okay. First one is from, the first one says, can you please hit the high note again for us?
We'll see if there's time at the end, okay?
Okay, I'll remind John for that. Yvonne says, wow, my favorite teacher and favorite topic. Mukobe says, I'm already enjoying the show. My favorite teacher and subject, Lishomo. I'm watching the show sitting with my mom. That's Hakani Rose. And there's a question from Mukobe saying, what is the difference between sound and ultrasound?
Okay. Guys, we didn't have time to get into that just at that point, but it's in the notes. Remember, there is a certain limitation in terms of the frequencies that human hearing goes to. Ultrasound is exactly the same type of wave as sound is, but it is in an area beyond our scope of hearing. And it can also be below on the bottom end as well. So in other words, we hear a certain number of hertz, from a certain number of hertz to a certain number of hertz. Outside of that is ultrasound. It's beyond our hearing. And both of those are useful for various things. Usually it's at the higher end of this sound spectrum, if you like, the higher frequencies that are useful for things like descaling teeth and all of that sort of stuff. But it's very useful for taking images. So pregnant ladies go for a scan, an ultrasound scan, and it's non-invasive. It doesn't affect the child, the developing child, and it gives the doctors a very good picture of what's happening by bouncing those off what's happening inside. They can also do it for tissue and for heart and all that sort of organs within the body, but it's mainly used for those medical purposes. That isn't the Doppler effect, though, so please be aware of that. Doppler and ultrasound are not the same thing. Doppler can be used in ultrasound when it's measuring the speed of something traveling towards you, like I said just now, blood. And they can measure the flow rate of blood in certain arteries. And so they can use Doppler to measure the speed of a tennis ball, all of that sort of stuff. Okay.
Nice one. Thank you, John.
Okay, thank you. Can we get on?
Your questions, yeah.
Okay, now guys, remember that these questions, Abby, just pass me that book, because we're really going to need to I don't think that you really like downloading notes, okay? So why not? Get all the notes in one book. This is where we are. We're in chapter 8 tonight. And we haven't got many chapters to go. But if you're wanting to have some peace for your revision, there we go. Get the book. And it's got all the solutions. It's got extra problems that we might not get to tonight. And it's got great summaries. So we're on page 128 this evening. And we're going to start with this first question. Question 1 actually comes from an exemplar paper. And I hope you can get the book, or at least for the moment, get the notes. But very soon, we're just going to have the books for you, and that's where you're going to need to get the stuff from. So let's get going. So during an experiment to determine the speed of sound, remember what they're trying to do? They're wanting to get speed of sound. So that's what they're trying to find. Learners are given a siren. A siren is one of those things on a megaphone that goes... You make the noise. Come, I can't do it now.
No, you can't afford me, John.
Okay, can't I afford a sound effect, eh? Sure. Okay, and it makes it of a single frequency of 426. 426 hertz. Remember, that's how we know its frequency, even though it says. And it does that, they attach it to a remote-controlled car and move it at a constant speed past a stationary tape recorder, which is mounted in the middle of a runway. Ignore the effects of friction, the tape recorded the sound. So here we go. There's the siren, and it's going one note, boop, all the way along. I don't know what that is. 426 is about close to C, but it's making one note. It's not going beep, bop, beep, bop, beep. It's not doing that. One note, okay? And there's the toy car, and it's moving past the microphone. There's the microphone, there's the tape recorder. So this car moves at constant speed, and it moves in that direction. So it's moving constant velocity, constant speed, and it's going along quite nicely. So the learners make the following observation. The pitch of the sound from the siren as it moved towards the tape recorder was higher than the pitch of the siren when it moved away from the tape recorder. So the first thing is they're asked to name the effect of this observation, and that in anybody is easy marks. It's the Doppler effect. Please make sure you don't just write Doppler, Doppler effect. That's the whole thing. So next question. In one of the trials, the speed of the remote controlled car was noted as 31 kilometers per hour. 2 notes from the siren, okay, were recorded. One with a frequency of 437 hertz and one with a lower frequency of 426. So that's the information they're given. Now look at what they've asked. The next question is to say, convert 31 kilometers per hour to meters per second. Very, very important. You must work velocity in SI units. And the SI units for velocity are meters per second. So how do we do the conversion? Some of you will say to me, oh, that's easy. You just put the one over the other and then you divide. No, do you multiply? But there's a number you divide or multiply it by. No, guys, that doesn't help me. I need to be able to explain it and put it very clearly. Yes, there is a factor you can check. It's 3,6. But let's see how we do it. The way I like to do it is I put 31 and I write kilometers and I put on the bottom here 1 hour. That's 31 kilometers per hour. We cool with that? Sure. Next thing, what must we change kilometers to? Well, we must change kilometers to meters. So how many meters are there in 1 kilometer, in 1 kilometer? We know that there are 1,000 meters in 1 kilometer, so I must multiply 31 kilometers by 1,000. That gives me 31,000 meters. Okay. Normally we don't worry about units. We don't put them into the equation. Here I'm doing it to show you how we're working with that. Now we need to change 1 hour into seconds. So how do we do that? Well, I know that in 1 hour there's 60 minutes. And each minute is 60 seconds. So I'm going to say 60 by 60, which is, if I use my calculator, and let's hope that we can get it. Just give me a second. Yeah, I know what it's going to do. It's not going to like me because it hasn't been turned off, but that's fine. I fixed it now. 60 multiplied by 60, and you can remember that's 3,600. I just wanted to show you where it came from. So there are 3,600 seconds in 1 hour. Now, what you can see is that you've got 1,000 on the numerator and 100 on the denominator, but we could even say make it 1,000 as well, and then that would become 3,6. And then you'd get 31 divided by 3,6, which is the short way of doing it. It's not the way that I want to do it. I'm going to do it the long way and show you that we get the same answer. So I'm going to go 31,000 divided by 3,600, and that gives me an answer of 8,61 meters per second. 8,61 meters per second. Excellent. We're ready to move on. So we now know the velocity of the car. It was moving at constant velocity. It now asks me question 1.3 to determine the speed of the car. So guys, let's put down all the information we've been given. What we're told is we've got the first thing that we were given way back in the front was the frequency of the generator. So we know the frequency of the source. We know that that was, look back there, right at the top, 426. 426 hertz. Now, we need the frequency of the listener, of the observer. Please don't panic here. You can use either one of these that are given, because there were two given. If you notice, it says to you that this one was at 437 and this one was at 426. So 426 was the lower one. I must use the higher one. So it actually didn't move past. It stopped when it came towards me. I must use the one that's different to the frequency of the source as the frequency of the observer. 437. 437 hertz. Now notice that this one is higher. So already I can say that the car from the diagram was moving towards. Okay, get it clear. That's why we're explaining it like that. Now, what other information are we given? We're told that the velocity of the velocity of the observer, the velocity of the listener, of the microphone, and all of that was 0 meters per second. And the last bit of information is the one that we've just calculated, and that was the velocity of the source, if I remember correctly, was 8.61. 8.61 meters per second. And it's moving towards the observer. Right, so I've got 4 pieces of information. If I go back to the equation, can use all of these. There's nothing much that I haven't got. So the only thing that I haven't got is the velocity of sound. And that's what I need to try and find. I haven't got that. So let me put down my formula. Like I said to you, I don't know that. That's what I want to find. But I still put down the formula as it was given in the data sheet. Remember, velocity, frequency of the listener, frequency of the source. Then there's the fraction bit. The listener goes on top, plus, minus, listener on top, velocity plus, minus, source at the bottom. So L always before S, reading from left to right, as well as from top to bottom. Make sure that you've got the formula right, copy it down correctly. Now what are we going to do? Well, the first thing I'm going to do is I'm going to substitute my values. Guys, don't try and pull things around and change the subject to the formula. For this one, it's really quite difficult if you do. But on top of that, if you make a mistake, you're not going to get any credit. So take the information that you've identified, all this information I've identified here, and we simply substitute it in. So we're going to say 437 is equal to velocity plus minus the listener. We know that was 0. Now, the next one, velocity. The source we know was moving. What was it moving at? It was moving at 8.61. Now, remember what we said. The velocity of the source, the frequency of the source originally was 426. So there we are. There's only one thing that I don't know and that I've got to work out here. Is that sign there going to be a plus or is it going to be a minus? And this is the crucial part of the whole system or the whole idea. We need to make sure that if that's the observer, notice that's bigger, then this one is smaller. Then this must be, the denominator here must be smaller. So that must be a minus. Let me say this again. We want this number here to be a number bigger than 1. Okay? Velocity of sound is in the numerator because plus or minus 0 is going to give me velocity of sound. Now at the bottom, I don't want velocity plus because that will give me a fraction, because then the numerator will be smaller than the denominator. I want the denominator to be smaller because I want this number here to be bigger than 1. Please get that right, because we are saying that the frequency, the observed frequency, has increased. Okay, so what's the next thing? Well, let's do the substitute, or let's do some of the things that we can do. And the first thing I'm going to do, I'm just going to take my equal sign out. I'm going to multiply through by the denominator on this side. So I'm going to say, here we go. We're going to multiply 437 multiplied by v minus 8,61 is equal to, now v plus or minus 0 is going to give me v, 426v. You agree? Hope so. Don't think it's too complicated at this point. What's our next step? Mathematically, what are we going to do? Well, we must multiply through by the bracket. So it just becomes an expansion. We're going to say we've got 437v minus 8,61 multiplied by 437. And I could just do that on my calculator. In a minute, I'll do it now. 426v. Okay. Let's do the calculation bit. We're going to say 8,61 multiplied by 437. 8,61 multiplied by 437 equals 3762,57. 3762. 3762,57 is equal to, now, have a look here. I've got 4, this was a minus, and this was a positive, but I'm going to take it to that side, and I'm going to say 437 minus 426. Put that in brackets, v equals 0. And I think you can see what the next step is. Well, let's do that, and let's say 437 minus 426 equals 11. So I get 11v over here is equal to 3762,57. And what do you think? Next final step, v equals 3762,57 divided by 11. Do it on the calculator and clear it. 3762,57 divided by 11, and we get the speed of sound in this experiment was 342 meters per second, 342,05, and if I'm doing to 2 decimal places, it didn't tell me how many decimal places, but I guess that I should really write it as 342,05 meters per second. Okay, there we go. We've worked out the speed of sound, given the information we have. Final question for this part. It tells me, give a reason why the observed frequencies are respectively higher and lower than the frequency of the source. So we were given the frequency of the source. Now, if you look over here, the one was 437, and the other with it was a lower frequency than that. It doesn't tell you what it was. Well, the one that was 437, it was when the car was moving towards the microphone. When it was moving away, it would have been lower, just like we heard when we spun the hose pipe or the pump pipe. Okay, so please remember that, but explain it fully. Make sure that you understand it. Guys, this one was unusual because it asked you to solve for velocity. Many of the others ask you to solve for either the frequency of the learner, of the listener at least, or the frequency of the source. You must make sure that you try as many. To try more, what are you going to do? You're going to get the book. Okay? Don't forget. Get the book, get the solutions, practice, work through it. The more you practice, the more exam revision type things you do, the better you'll become at this section. And guys, can I appeal to you? Please don't forget term 1 work. Very soon you're going to be heading for prelims. Make sure you tidy all those areas up. Do as many mechanics questions as you can now as well. Okay, Abby, I think it's time for a break.
Thank you so much, John. Guys, you can get the workbook by simply sending an email to sales@mindset.co.za. And John, before we go to this break, Lebogang Maboka says, please wish me a happy birthday today, once in a lifetime. Please, Abram. So happy birthday to you, Lebogang. I hope we've just made your birthday extra special by mentioning you. Hope you enjoyed it, and all the best with your studies. Guys, we'll see you after this break. Welcome back, awesome matriculants. Now, you probably know by now that we've got an exciting competition, the Be a Bright Spark competition. Entering is simple, guys, and you could be a winner of the Chevy Spark L and drive your way around just like Dimakatso, who won the first cup. So the second car could be yours. Simply buy yourself the K53 the Safeways K53 manual, or download the cool Android app, which is available from the Samsung Galaxy App Store or the Google Play Store. And it's available for only 59 Rand from Google Play Store, guys. So after that, you go like our Facebook page, which is facebook.com/LearnExtra, and also the Safeways Facebook page. Then after, fill in the entry form, and your name is in the box, and you could win. John?
Just remember, guys, if you entered last year, you're still in the draw. So don't give up. You can enter. Can they enter again?
Yes.
Yeah. Enter again. Do another. Yeah. Get going. Make sure that you stay on top. And stay watching the competition, because it's a really great competition.
Who doesn't want a car?
Who doesn't want a car? Who doesn't want accommodation? Who doesn't want a workbook? Hey, we give away great prizes on this show. So, guys, it's all about learning. It's all about having fun and making sure that you understand things. Ask questions. We'll take some of your questions just now. But here's my question for you. By the way, Lebogang, happy birthday. I know that you're not 25, but this scientific tool, or I hope you're not 25, but this scientific tool that had a birthday a couple of days ago, what was it? Well, did we get some answers?
Everyone got it right.
Got it right. Have a look what it looks like. There it is. It's the Hubble Space Telescope. Now, the next part of the question was, what's the connection between the Hubble Space Telescope and our topic of the Doppler effect? Did anybody give us an answer?
I don't think.
Okay, you just have a
that, John.
You go and look there,
Yeah.
and let's talk a little bit about the Hubble Space Telescope. So the Hubble Space Telescope was launched on one of the space shuttles, and guys, they made a little bit of a mistake, but it was a bit late. It stood up about 500 kilometers above the Earth's surface, went to take a picture of some star patterns, and it found it was all fuzzy. It was like they needed glasses. And that's exactly what the NASA scientists did. They, over a period of time, repaired the mirror and the lenses of the Hubble Space Telescope, and so that we've got some of the most amazing shots of the universe around us. I just want to show you some of them. So there's a close-up picture of Jupiter. And they've tracked Jupiter over a period of time as well. And one of the famous features on Jupiter was the red spot. I haven't highlighted that very well, so let me just do that again. Around that red spot, there were some things that were increasing in size, decreasing in size, and they were able to track it using the Hubble Space Telescope. An amazing clarity of what's around us. But this is probably the most famous image of the Hubble from the Hubble Space Telescope. It's absolutely magnificent. And let me just scroll down while you look at it, and you'll see that this is known as the Pillars of Creation. the image is a little bit big for the board, but it is just amazing, a place where there are new stars being born all the time, and it just gets so exciting that this was not seen before we had Hubble. Now, the reason for that is that there's a whole lot of atmosphere between us and space. When Hubble is 500 kilometers above the surface of the Earth, able to see into space, there's no distraction, there's no interference of light. Light becomes much sharper, and they're able to identify things in space. I just find astronomy amazing. Here's another amazing picture. You think that this is a cartoon from some anime movie? No, it's not. This is real stuff. This is an image that the Hubble Space Telescope produced. It's of a Horsehead Nebula. But the interesting thing here is that they're using infrared to track. This isn't cloud. These are gas clouds. It's not water cloud. And there are billions and billions of stars evolving in this nebula. So really great stuff. Exciting to be at the cutting edge. And if you're not excited about astronomy, you need to get excited, because South Africa is at the cutting edge of astronomy as well. We've got one of the greatest astronomical experiments going to be launching very soon, and that's the Square Kilometre Array. But I won't get too excited and won't get off topic. So, next thing, this is also from the Hubble Space Telescope. What's it? Not just a nebula of stars and showing you where stars are. This is a galaxy. This is even bigger. This is even more wonderful and more incredible. The Whirlpool Galaxy beyond us, thousands and thousands of light years away. And if you want to find out more about Hubble, go to this website. Maybe if you can pick it up, Hubble 25th, and you can download presentation, and ebook is there for free. I'll see if we can even put it on our website, so you can pick it up as a news article tomorrow. Okay, so that's Hubble. But why am I excited about Hubble when we're talking about the Doppler effect? Here it is. Hubble and the Doppler effect. Now, you need to understand something before we get into the detail. First thing you need to understand is that every element on the periodic table, you say, oh, we were doing physics, I thought we weren't doing chemistry. No, we're doing chemistry and physics together. So every element on the periodic table has a unique signature. And we can either see that as a set of lines called atomic emission spectra, or a set of lines called atomic absorption spectra. I'm not going to explain it more than that, just to say it's the signature of every element. Whether the element is here on the Earth or whether it's in the sun, it's the same signature, same elements all around the universe. We can identify new elements, and in fact, elements were discovered that weren't on Earth originally because they looked at the spectra. So here's an example of a spectra. Normally we would see orange or red all the way to purple, and we wouldn't have any of these black lines in it. But these are signature lines for a particular element. Now, I don't know what element it is, I'm just illustrating a point. So this is the normal one. This is the one in the lab, the top one. What I want to show you is that if we get this arrangement where the lines aren't in line with each other, but rather they've been moved, in which direction were these two lines moved? You see, that's an idea, that's a characteristic. That's a particular characteristic. That double line there is a particular characteristic. And that one's a particular characteristic. And that one's a particular, and it's now been moved. The color should change as well a little bit, but it's been moved downwards. In which direction? It's been moved towards the red side. In other words, we say it has been red shifted. So the line isn't where it was before. It's been moved to a lower frequency. Okay? And if it's moved to a lower frequency, then what does that mean? Think about it. Is the object that is emitting that light moving towards me or away from me? Remember what we said. When it moves towards me with Doppler, the frequency is higher. If it's moving away, the frequency is lower. the frequency of red light is lower than the frequency of blue light. So if it's been redshifted, it's got a lower frequency, and if it's got a lower frequency, we can say it's moving away. And if it's moving away, Hubble is picking up that the majority of the stars at the edge of the universe are moving away. So what's that telling us? The universe is expanding. We call that the red shift. If we suddenly found that there were elements that were blue shifted, and it can happen within a certain area, then we would say, oh, we've got some stars in galaxies moving towards us, or we're moving towards them. Okay, so majority of the time, this is the empirical evidence, a very important thing, goes back to us understanding that cosmology has this theory that in the beginning, we found that there was an expanding universe. Stars that erupted and spread, energy that exploded to create galaxies and universes and possibly other planetary systems, which we're starting to identify now. We're picking it up because Hubble has confirmed that things very far away from us are redshifted. Isn't that interesting? Well, I hope you find it too. Could even come up in your exam. Now, you're not going to need to do calculations with light because the speed of light is constant on Earth, and we won't need to change the speed of light. There are different rules that apply, laws of relativity. But what you do need to understand is that when we're talking about the universe, then we can get a phenomenon like called redshift. You had some questions.
Yes, here's the first one from Mukove saying, what happened to Mukove's question? Okay, Mukove is saying, which direction does the frequency move if it's greater than 1?
Okay, let's be very clear. So remember, I think this is what you're referring to, Mukove. You're saying this part here, if this part here is bigger than 1, so this one is bigger than 1, then look at it for me. This is bigger than 1. Then this was the original frequency. So this is the original frequency. That's the source. And if the thing in brackets is bigger than 1, then the observed frequency is going to be bigger than this one is going to be bigger. Because anything multiplied by a number bigger than 1, then we can say this is going to be bigger than the frequency of the source. Okay? Because if we take bigger than 1, 1.5, so we start with 200, we multiply by 1.5, it's going to be bigger than 200. Okay? What is that telling me? If that bit in brackets, then it tells me that the object is moving towards. It's moving towards the source. Either the listener or the observer is moving towards the source, or the source is moving towards the observer. Okay? Smaller, then it's going to be the other way. Then the observed frequency is going to be smaller. It's going to be redshifted. Okay?
Nice one, John. Because of time, we won't have time for another question.
Oh, no. Well, guys, I hope you get your pipe out and let's give it a whirl. Okay? Make sure that you go out and kill Doppler.
You said you were going to give me the high pitch one.
Oh, no, we didn't get a chance. No, I didn't pull it up.
Okay, John, I don't want you to kill yourself live.
No, I'll try not to. Eh?
Right.
Okay, great being with you. We'll see you again.
Thank you so much, guys, for watching. And happy birthday to Asanda as well. Said she was afraid to say it's a birthday. Guys, we love you and see you some other time. Peace.